That's right. All right, we're recording, guys. Hi. All right, so uh, today we're looking at section 5.2, but like I said, just the first half of it. So we're dealing with properties of rational exponents. So we're going to be looking at what we talked about yesterday, but digging in a little deeper question. Okay, we'll deal with it. All right, so there are some properties of exponents that you guys have actually looked at before quite a bit, and we're just going to spend a little bit of time here at the beginning reviewing what those are, because those can all be applied to these rational exponents that we've been looking at, or at least started looking at yesterday. Okay, so, and I'm just going to write them all down because I think it's important for you guys to just have them in your note as kind of a reference, so that when we need to simplify things later on, you can come back to this list and kind of check and see, are there any of these that I can use, and that sort of thing. So, and each one of them has a name. So the first one we're going to look at is called a product of powers. And a product of powers basically says that if you have two powers, so a to the m times a to the n, and they have the same base. They're both a, right? It's the same number raised to two different numbers, and you're multiplying them together, you can turn it into just one power, okay? What do you do with the m and the n to put this into just one? Yeah? Nope, you don't multiply them. You add them together. You add the powers. So this is a raised to the m plus n, like that, okay? So if you had, let's say, like as an example, 2 to the third times 2 to the fifth, that would be 2 to the eighth. You don't multiply the 2's. Okay? Now the reason that one works, think about it this way, like this 2 to the third times 2 to the fifth. 2 to the third is 2 times 2 times 2. There's 3 2's there. 2 to the fifth, 2 times 2 times 2 times 2 times 2. There's 5 2's there. How many do I have altogether? 8. Okay? So 2 to the eighth, because there are 8 of them that I'm multiplying together ultimately. Yeah?
I understand you're just doing the powers to the
Yeah. That's what I just explained. Because this 2 to the third is telling you multiply 2 3 times. And this is saying multiply 2 5 times. If I'm multiplying the multiplyings together, it's just one giant multiplication problem with 8 2's in a row. So it's 2 to the eighth. All right? So, yeah. So it's a real common mistake to take the bases and multiply them and then also take the powers and add them. All you need to do is take the powers and add them, and that's it. Okay? So, that's a product of powers. Now, this also works for powers that are fractions. So, like we were looking at the other day, what if I had something like 7 to the 1/4 multiplied by 7 to the 1/2? What would that be then? Careful. Nope. What's a fourth plus a half? 3/4. Yep. You add the exponents, right? Just like 3 plus 5 is 8. 1/4 plus a half is 3/4. Okay? Because it's 1/4 plus 2/4, right? Which is 3/4. So, yeah, adding fractions. Yeah, got to know how to do that, guys. All right, so product of powers, that's what that one is. We also have a quotient of powers, which is very similar. What's the word quotient mean?
The product of a division.
The answer to a division problem, right. So a quotient of powers, kind of the same rule, except this time we are dividing the 2, so in the 1 that we pull together, we actually subtract. Yeah. So it looks like that. A to the m divided by a to the n is a to the m minus n. So, do a couple of quick examples of this thing too here. So if we had like oh, sorry, this should be a division. So if we had 3 divided by 3 to the 5th. Okay, so when I write just a 3, it's a power of 1. So what's that going to be equal to then? 3 to the negative 4. Because 1 minus 5 is negative 4. Yeah. Okay. So again, you're not doing anything with the 3's, right? You're just taking the powers and subtracting them then. So, and again, if it's easier to think of that as a 3 to the 1st, 1 minus 5 is negative 4. So it's to the negative 4. And what we learned from yesterday, you could take this thing then and make it 1 over 3. That's a little tiny 4 down there. Sorry, it's really small. But you could make that 1 over 3 to the 4th power too, technically, right? Because it's a negative exponent. But anyway, so that's how that works. And again, it's also true with fractions. Let's see if I can give you one here that's got some fractions we can work with. Okay, so if I have x, and that's a 7/8 divided by x to the 3/8. So it would be, you subtract those two, it's 4/8, right? So x to the 4/8 or x to the 1/2 then. And then based on what we learned about yesterday, what's another way I can write x to the 1/2? It's not a negative exponent, it's a fractional exponent. What are those? Square root, right? 1/2 power is a square root, a 1/3 power is a cube root, a 1/4 power is a fourth root, etc., 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 right? So that one would come out like that when you're done. All right, so that's quotient of powers. Again, all you're doing is subtracting the exponents, right? Here's one we've actually talked about in here already. Power of a power. So that one's going to be, like if you take something that's a power, a to the m, and then raise that to another power to the n. That simplifies with the multiplication. So a to the m to the n is the same thing as just a to the m times n. You multiply powers together. We actually used that idea yesterday in our notes to help come up with some of the relationships between the fractional exponents and the roots. Okay, so for example, what would be 5 to the 1/3 squared? What do you do with the powers? You multiply them. Okay, so what's 1/3 times 2? 2/3. Yeah, don't overthink it. It's 2/3. That's it. So 5 to the 2/3 would be that one. Okay. Just the numerator. Think of it as like when you're multiplying 1/3 times 2. 1/3 times 2 is really 1/3 times 2 over 1, which is 2 over 3. Okay, so that's what you're doing there, yeah. Okay, next one that you guys have seen before. Power of a product. Not to be confused with product of powers. All right, so this one says if you have two numbers multiplied together raised to a power, you can break it apart like that. A to the m times b to the m. It's kind of like the distributive property of exponents, okay? If you have something in parentheses like that where you're multiplying things together, you can take a power and bring it in and do the power to each piece individually. Now, that being said, if this little symbol right here was not a multiply, Caleb, but instead was a plus sign, it's a big no-no. You cannot distribute in like this if this is a plus sign. If it's multiplying, it's okay. But you can't distribute exponents to something where you have plus or minus, that sort of thing. Yeah, you'd have to just leave it. So, example of this one. Let's say we've got... Usually this one works the opposite direction. So let's say we've got 2 to the third times 5 to the third. Okay, so like I said, I'm kind of going backwards. I'm starting over here, right? So how could I rewrite this? How could I condense this down into just one power?
2 times 5 and first
Okay, and what's 2 times 5? So that's actually 10 to the third? Okay. Doing that with some fractional exponents, it doesn't really change the game very much here. So if I had like x to the 1/2 times y to the 1/2. Xy to the 1/2. And again, what's a 1/2 power? Square root. So this is actually the square root of xy then, right? Yep. Okay. So that's power of a product. We also have power of a quotient. Okay. Same idea. So if you are dividing two things, you can break it apart the same way. Okay. All right, so do one quick example of that. And again, I'm going to go backwards with this one too, because usually that's how you see this one done. So if I have 6 to the 2/3 divided by 3 to the 2/3, okay, what is that going to be then? 2 to the 2/3, right. You just divide the two numbers, the two base numbers. So it's 2 to the 2/3. Yep, exactly. All right. So that's power of a quotient. Like I said, works pretty much like power of a product, except you're dividing instead of multiplying. So, all right. And then the last two, these are ones that we also talked about yesterday, but we're kind of more formally getting these things down. So there's the negative exponent property. So if you have a to the negative m, that's equal to 1 over a to the m. And then there's the zero exponent property. Which we talked about yesterday. Anything to the 0 power is always what? 1. Yeah, it's always 1. Okay, so those are all your different properties of these things that you've used in the past, and now we're using with fractional stuff too. Product of powers, quotient of powers, power for power, power for product, power for quotient, negative and zero exponents. Okay, so, and we did some little examples through there, so I'm going to just kind of leave that be. Figure we're good. Nope. So properties of radicals. What? Oh, okay. Now these we're going to use to help us through the rest of what we're going to do today. We got the product property of radicals and the quotient property of radicals. It basically directly relates to some properties that we talked about up in the top here. Okay, but these are just written out with the radical symbols, and I think are a little bit more useful to see this way because this is how you're going to be actually writing them. All right, so you've done this with square roots before. Maybe you don't remember it. I'm not sure, but you've done it with square roots, but now we're going to use it for nth roots. So any root, could be a square root, could be a cube root, fourth root, whatever. It always works. So if you have two separate roots, but they're the same kind of root, so they're both square roots or they're both cube roots or whatever, you can put them together into one. You multiply them together, you can put them together into one. The quotient property, it's the same idea. If you have two separate roots that are the same type of root, you can pull them together into one. So I'm going to write it like this, I think. So if you have two separate roots that are dividing, but it's the same kind, then you got the nth root of a over b. It becomes just one big root. That is the quotient of those two things. Okay, so do a couple examples of this, and then we'll get into how we're actually going to apply this stuff. Okay, so all right, so let's say we got the cube root of 12 times the cube root of 18. So using the product property, what's that equal to? All right. That's the cube root of 216 because 12 times 18 is 216. And what is the cube root of 216? 6. Yeah, good. Okay. So the cube root of 12 and the cube root of 18 both come out to, those aren't cube roots we can do by hand. We don't know what those are without getting decimals or whatever from a calculator. However, the cube root of 216 we do know. So this is one way where you could take something where maybe you weren't able to figure out the answer by hand, but by combining them together you can. You get a number that you can actually take the cube root of, and the answer is 6. Let's do another one with a quotient real quick here. If we had the fourth root of 80 divided by the fourth root of 5. There is no fourth root of 80 that's a nice integer, and there's no fourth root of 5 that's a nice integer either. However, if we do follow the quotient property here, what is the fourth root of 80 divided by the fourth root of 5? Fourth root of 16, right, because 80 divided by 5 is 16. So I bet you can do this in your head. What number multiplied by itself 4 times gives you 16? And it's 2, right? Okay, so that's kind of using those properties, okay, in that way, where you can combine them into a new root all by itself, which you might be able to then figure out what the answer is through that, okay? So what we're going to finish up with here today are simplest forms of a radical. Okay, so simplifying some square roots and cube roots and stuff like that. And we're going to use those properties that we just talked about to help us do this. So if you have some kind of root and you need to write it in simplest form, there's 3 criteria that it needs to meet. Okay? And we're going to write down what these 3 are and then work through actually doing that. All right, so first things first, though, we need to know a little bit of lingo, okay? Some vocabulary. The little symbol that goes around it, the square root or what have you, that's called the radical. The number or variable that is underneath the symbol is called the radicand. All right, so I'm going to be using some of that vocabulary as we move forward here, but that's what those are. The symbol is called the radical. Whatever's underneath it is called the radicand. So to have one of these radicals in simplest form, some things have to be true about what the radicand is. Okay, and the first criteria that has to be met is that no radicands have perfect nth powers as factors. Okay, so what in the world does that mean? Well, like I said, you've done this with square roots before, so let me give you an example to start off with here that involves a square root. Square root of 20. We're going to use the product property in reverse to simplify this thing. Okay, so it's a square root. Are there any perfect square numbers that are factors of 20?
No.
Yes, there are.
Yes, there are.
4.
Okay.
Right? 4 is a perfect square number and it goes into 20.
Are there any numbers that if you square them, it goes into,
Oh.
like if it's a perfect square root?
So, you guys remember doing this before? Okay, so do you guys see how this is the product property of radicals and just in reverse, right? I've taken a square root and I've broken it into 2 square roots instead of putting them together and making 1. Okay, one of those 2 square roots now, I know the answer to, right? Square root of 4 is 2. So this thing simplified is 2 times the square root of 5. So I know it's weird, but this is considered simplest form and this is not. Even though square root of 20 seems a lot easier to look at, seems simpler than writing it like this, okay? But that square root of 20 is not meeting this first criteria. Its radicand, which is 20, has a perfect nth power as a factor of it, and that perfect nth power is 4. Okay? So because it's a square root, we're looking for perfect square numbers that are underneath there. Okay? Now, what if I had something that was a cube root instead of a square root? So something like the cube root of 54. Now I'm not concerned with perfect squares, I'm concerned with perfect cubes. Okay? It's a perfect nth power. Well, n is 3 now. So what are some perfect cubes that would go into 54? 9's not a perfect cube, it's a perfect square. So 9 I don't care about this time. 8 does not go into 54. 6 is not a perfect cube or a perfect square. So 27. Good. All right. So I did this. I knew you guys would be giving me lots of wrong answers. I kind of set you up for that. Sorry. Because what this tells us is we need to do a better job of knowing perfect cubes, right? Because that's where we're struggling. We don't really know what the perfect cubes are. So I'm going to go off to the side here before we actually finish this one up. Let's go off to the side and let's make a list. We're going to make a list of perfect squares. We're going to make a list of perfect cubes. We're going to make a list of perfect fourths. And I think we're going to stop there because you get much higher than that and it gets crazy. But perfect squares you guys are really, really used to working with. Okay, so numbers that are perfect squares. We're going to skip over 1 because that's not helpful with this stuff. So what's the smallest number that's a perfect square? 4. Okay, what's the next one? 9. Keep going. 16. 25. 49. 64. 81. 100. Etc. You could keep going. 121, 144, blah, blah, blah. Okay. All right, so we're good with those. So what about perfect cubes? So these are all numbers that you can get by multiplying a number with itself 3 times. Okay? So 1 is a perfect cube, yeah, but that's not helpful. So what's the next one? 8. 2 times 2 times 2. That's 8. That's a perfect cube. Okay, what's the next perfect cube? 27. 3 times 3 times 3 is 27. Okay, next one. 64, good. 4 times 4 times 4 gives you 64. 125, good. 5 times 5 times 5 gives you 125. And then 216. We'll stop there. I think much past that it gets nuts. All right, so those are perfect cubes. All right, and then we'll make a short list of perfect fourths. Okay, these are all numbers that you get by multiplying a number with itself 4 times. So 1 times 1 times 1 times 1, okay, that's 1. That one's not helpful, though. So what's the next one? 16. 2 times 2 times 2 times 2. That's 16. That's a perfect fourth. Okay, what's the next perfect fourth? 81. 3 times 3 times 3 times 3 is 81. Okay, then let's just 256. All right, we'll stop there. All right, do you see how these are blowing up huge really quickly? Okay, perfect fifths will get even larger even quicker. Okay, so I'm not going to make you go above a perfect fourth, and I'm not going to make you go any further than these lists went. Perfect squares, maybe. Like 11, like if 11 squared is 121, 12 squared is 144. Like you should know those at this point. 13 squared is 169, I think. Anyway, let's go back to the problem though. So if you're trying to use this method that we did with this square root for a cube root, we ignore this list. We're not concerned with perfect squares because this is a cube root. We're concerned with this list. So do any of these numbers go into 54? And when someone had already said it, 27, right? So, cube root of 27 times cube root of 2 would be how we break that one up, right? Because 27 times 2 is 54. Okay, and so then take the cube root that you know. What's the cube root of 27? 3. So this becomes 3 times the cube root of 2. We have simplified that cube root. All right, let me do one more of these with you guys. See if you can do this without me. I'd like you to simplify the cube root of 500. And I'll freeze it here. All right. Here's what we got. Should be 5 times the cube root of 4. All right, you guys all catch 125 goes into 500 4 times. Okay, so we take 500, break it into 125 times 4. So it's 5 cube root of 4. And again, be careful, you're going with the cubes list, not the squares list. Yes, 100 does go into 500. However, that's a perfect square, not a perfect cube, so you'd have to look at this list instead. So, yeah, so that one will work. Okay, so that's that first criteria. No radicans can have perfect nth powers as factors. You gotta break them down, like we just did there. Okay. Criteria number 2 and number 3 actually go hand in hand. So I'm going to list these off together, and then we'll kind of go through how those work. So the second issue, no radicans contain fractions. So we were good with all of these up here because none of those were fractions, right? But in general, a radicand cannot contain a fraction. All right. And in dealing with that, you're going to run into this issue that you have to resolve, which is no radicans appear in a denominator. Okay, so we're going to use that quotient property now to help us deal with this. Okay, so we've got the no radicans contain fractions, and then they don't have any appear in the denominator. So let's go back to square roots, because those are easier. Let's say we have the square root of 2/3. Okay, not in simplest form, right? Because there's a fraction in there. So I can use my quotient property of radicals, though, to alleviate that problem. And if you remember, I'm allowed to do this. Right? If I have a square root of a division, I can break it into 2 separate radicals divided by each other. Okay? So, no radicans contain fractions. I'm good there, right? I have 2 radicans this time. One of them's a 2, one of them's a 3. Neither one of those things are fractions, so that's fine. That's all well and good. Now I'm in trouble with number 3, though. No radicans appear in a denominator. I have a square root of 3 in my denominator. That's bad. Okay, so I gotta take care of that problem then. Okay, so to take care of that problem, we have to rationalize that denominator. You guys have probably done that before. You did this in Algebra 1, I'm sure, at some point, where you multiply by the square root of 3 over the square root of 3. Now, before I do this, okay, just want to verify with you guys here that I'm not actually changing the value of the number that I'm messing with here, okay? Square root of 2 over the square root of 3, I'm multiplying that by square root of 3 over square root of 3. What am I actually multiplying it by? 1. When you multiply something by 1, are you changing its value? No. So whatever I get here when I'm done with this multiplication, I can know for certain that it is equal to what I started with, right? I'm not actually changing what the value of the thing is. I'm just rewriting it in a different way. And this is a convenient way to take care of that. Okay? So, let's go ahead and multiply these together. And I'll try to prove to you here why I chose square root of 3 over square root of 3 and see if it makes sense. So if you multiply fractions together, remember you do the numerator times the numerator, and then the denominator times the denominator, okay? So, square root of 3 times this, or I'm sorry, square root of 2 times the square root of 3 is what? Square root of 6, right. And the square root of 3 times the square root of 3? Square root of 9. Which is a square root we know, right? Which is just 3. So we've got square root of 6, 3. Okay, so let's take a look at my 3 criteria here. Do my radicans have any perfect nth powers anymore? It's the square root of 6. Are there any perfect squares that go into 6? Nope. Do any of my radicans contain fractions?
Nope.
Does the radicand contain a fraction? Nope. It's 6, right? Okay. Are there any radicans in any denominators? Not anymore. Okay? This is now just a 3. It's not the square root of 9, it's a 3. So I'm good. This is simplified. Good question. Why did I use that? Why did I use the square root of 3 over square root of 3? I used that one because I knew if I multiply the square root of 3 by itself, I'm going to get a perfect square number right there every time.
So if it was like something else, like square root of like 3 over the square root of 4, then would you do like, oh wait, no, that doesn't work. Square root of 4 is it?
Let's say I had like square root of 2 over square root of 5 instead. Then I go square root of 5 over square root of 5, but then I knew that my denominator would end up being the square root of 25, right? Because 5 times 5 is 25. So I'm always getting a perfect square on the bottom, no matter what. No matter what the number is, if I choose that whatever's in the denominator to be the thing that I use to make my fraction next to it, that denominator is always going to be a perfect square that I can take a square root of, and I'm good. Okay? So that's why I chose that, because I knew it would work out so that my denominator wouldn't have a radical in it anymore, and I'd be all set. Okay? So let's do another one of these, just so you guys can practice the process start to finish here. So why don't you try on your own square root of 1/5? Okay? Works the same way. So simplify that square root. Okay, so did you get that? Okay, square root of 5 over 5. No more fraction, and no radicals in the denominator anymore, because it's just 5. Okay, so what if we were dealing with a cube root instead of a square root, though? The game changes just a little bit. I'll give you an easy one, then I'll give you a hard one, so that you get the idea first, and then you can work on dealing with difficult ones second. Okay. So anyway, so cube root of 7/8. If we approach this the same way we did the last one, we can break it apart into 2. Okay? That's still the same idea. This is still using that quotient property. Taken care of my second criteria. No radicals that contain fractions. Good. It's a cube root of 7. It's a cube root of 8. There's no fractions in either one of those. I'm fine. But I still have a radical in my denominator. But, exactly, the cube root of 8 we know, right? It's 2. So this one actually works out kind of nice. Cube root of 7 over 2. And now I've got everything taken care of, so I'm good. I'm done. Now what if it didn't work out?
Once you just times it by like that, the same number squared, the square root of the same number.
You're on the right track. Let's try this one. Cube root of 2/3. Okay? So we end up with the cube root of 2 over the cube root of 3. Now, from here, if I did the same thing that I did with my square root, it wouldn't quite work. If I just said, all right, I'm going to take the cube root of 3 and I'm going to multiply by the cube root of 3 over the cube root of 3. In that denominator, what would I end up with? Say that louder, Sam.
9.
Cube root of 9, right? Now, if it was a square root, no problem. That's great. It's a cube root, though. Is there a cube root of 9 that we know that works out nice and even? No. It's a cube root, yeah. Okay, so I can't do that anymore, right? What I need to think about is, okay, so if I can't multiply just by the number that's down there, what can I multiply by so that when I'm done I have a perfect cube? 9. 9 times 3 is 27, and 27 is in that list of perfect cubes, right? So you got to come up with a number that you know will work if you multiply and give you one of those perfect cubes in that list so that the bottom can work itself out then. So I'm going to multiply by the cube root of 9 over the cube root of 9. So now I have the cube root of 18 over the cube root of 27. And like I said, the cube root of 27, we know what that is. It's 3, right? So we've got the cube root of 18 over 3. So that works. Okay, that's in simplest form. And that 18, can I break down that 18 anymore?
No.
Any perfect cubes that go into 18?
No.
No. So I'm good. So and that's something else. Like if you end up at this stage and that top root, whatever it is, could continue to be broken down if there happen to be nth root factors still sitting in that thing, you'd have to take care of that still. But 18, there's none of those perfect cubes that go into 18, so we're okay. We're done. All right? So this is just the first half of this section. All right? So we're done for today, but we're going to do some more of this stuff on Thursday. So here's what I would like you to have ready for Thursday. Have this complete by Thursday. You got 2 nights to do it. So 3 to 27, that much. I think you can. Where did it go? Oh, there it is. Okay, we're ready. All right, so yesterday we talked about some different ways that you can write roots so that they're in simplest form. Today I'm going to continue on in that vein here with our first example. And think about the 3 different criteria that I talked about yesterday about what you need to have a simplified root. And see if you can tell me what's wrong with this one to begin with and what we need to change. Now that looks a lot different than the types of things that we were looking at yesterday, but take a look. Go back in your notes if you need to. Page back for a second. We had 3 different criteria that we wrote down yesterday about what we need to have if we're going to have a root that's in simplest form. Which of those 3 rules is this one violating? Yes? Correct. That third rule was you can't have any radicals in the denominator. Okay? Now, the way that we took care of that yesterday was that we would, at least with square roots, we needed to multiply both the top and the bottom of the fraction so that what we had at the bottom of the fraction was a perfect square so that we could then square it and it gets rid of it and it's not a root anymore. Okay? Now this one, we can't do that. Because if I were to multiply both the top and the bottom of this by, say, the square root of 5, I would have to distribute the square root of 5 into the denominator, in which case I'd still have a square root of 5 floating around in there by the time I was done. Okay? So we have to do something else. We're still going to multiply by the same thing over itself, but today we're going to multiply by this thing called a conjugate.
Great. More big words.
More big words. You don't need to remember the word conjugate so much as understand how it works. Yes, it's supposed to be minus. Okay? A conjugate is the same as what you had before, except the sign in between the root and the whole number has changed. So the conjugate of 2 plus the square root of 5 is 2 minus the square root of 5. So we multiply by the conjugate over itself. So essentially, I'm still just multiplying here by what? 1. Okay?
That would be 1, correct?
Mm-hmm.
So it would just be 1 times 3 over 2 plus the square root of 5.
Yeah, so I'm not changing the value of the thing, but when I'm done multiplying this through, I'm going to have something that looks different. And it's going to be in that simplest form so that we don't have a root in the denominator anymore when I'm done. Okay? So let's go ahead and actually multiply this stuff together, and I'll show you why the conjugate works. Okay?
So it's just the denominator and then you change the sign.
Yeah. Yeah. All right, so when you multiply fractions together, it's numerator times numerator and denominator times denominator, right? So numerator, I got 3 multiplied by 2 minus the square root of 5. And then in my denominator, I've got 2 plus the square root of 5 times 2 minus the square root of 5, like that. And now I have to actually start, distributing everything when I multiply those. Okay? So in the numerator, if I distribute the 3, what am I going to end up with there? Nope. It is a 6 to start with, though. You can't multiply 3 with the root 5. It has to be 3 root 5.
We're getting into some crazy stuff now.
Okay? Because 3 and the square root of 5 are not the same thing. Okay? They're not, in a sense, like terms. Think of the square root of 5 as like an x. Okay? It's like a variable of sorts. So it'd be, if you had 2 minus x, it would be 6 minus 3x, right? But since it's the square root of 5, it would be 6 minus 3 square root of 5. Now in the denominator, I got a FOIL. I got a binomial and a binomial multiplied together here, okay? So let's do that multiplication here real quick. 2 times 2 is 4. 2 times negative square root of 5. And then square root of 5 times 2. And then square root of 5 times square root of 5. Okay, so that's all in the denominator. But there's a ton of cancellation that happens here now. If you take a look at that, what do you notice? I said there's a ton of cancellation that happens in the denominator.
In Athens. Like Athens, Greece? Whoa. Now we're getting into some geography?
All right, so somebody give me one thing that you notice about that denominator. What's going to happen here now to make it simpler? Yeah.
2 square root 5 cancel out.
Right, because one's positive and one's negative, so these 2 in the middle are gone. Okay, anybody else notice anything else that's going to happen here now?
Oh, 25.
Yeah.
Yeah, 25 is going to be 5.
Yeah, the square root of 25 is just 5. So what I've got going on here now is 6 minus 3 square root of 5 still on top. And then on the bottom I have 4 minus 5. Because the 2 middle ones canceled out and the square root of 25 is just 5. Okay, well, what's 4 minus 5?
Negative 1.
Negative 1.
Raise your hand. No.
Shh. Okay, so I've got 6 minus 3 square root of 5. And that negative 1, if I divide everything on the top by negative 1, that's just going to change all the signs, right?
Right.
Question?
Hold on. So, before you, when you cancel them out,
Mm-hmm.
Yeah. Alright, so you got 4.
Mm-hmm.
Oh, never mind.
You get it?
Yeah.
Okay. Alex, question?
So, wait. When we square root the 25, we're only doing the bottom, the denominator, and nothing with the numerator.
Nothing. Yep, we're just working in the denominator there. All right, so our final answer here is going to be negative 6 plus 3 square root of 5.
No. Minus. Wouldn't be negative the square root of negative 5?
Nope.
It's divided by negative.
3 square root of 5 is one term. If I multiply that by negative 1, it is negative 3 square root of 5. So if it's negative 3 square root of 5, I'm just switching that back to plus. So negative 6 plus 3 square root of 5. That's it. Okay?
I understand why you like switching signs.
I divided each part of the top by -1. 6 divided by -1 is what? -3 divided by -1 is what? +3, right? So +3. Okay. Again, think of square root of 5 as just like an x, like a variable. We're not doing anything to that. It's just sitting there. Okay. All right. So that's using a conjugate to simplify. All right. Now the reason that it works is because if you choose the conjugate, opposite signs, guys, pay attention to me. If the snacks are becoming a distraction or whatever, then let's not do it. Okay. Well, I don't know what's going on over there, but for whatever reason, people keep turning back away from me. The reason that this works is because they have opposite signs. Okay? These two in the middle over here would never have canceled out if they didn't have opposite signs happening here. You guys see that? And if these two are still the same, square root of 5 and square root of 5, I'm guaranteeing I'm getting a perfect square right here. In which case, I'm going to have just two whole numbers here that I can add or subtract depending on what I got there. Okay? So that works out. Yeah?
So if the very first thing was 2 minus the square root of 5,
Mm-hmm.
would the two things be 2 plus?
Correct. Yep. Okay, let's do one more of these just to make sure you got it.
So what kind of math would you call that? Like conjugate?
It's called conjugation.
Conjugation?
Conjugation. Mm-hmm. Kind of like in English class, you have conjugation, right? Conjugate the verbs. We conjugate the rational expressions.
I don't pay attention to anyone. I'm basically a rebel. I'm what they call a rebel.
Okay. So, try that one, okay? I want you to take that one as far as you can on your own. All right, give you like 5 minutes maybe.
Well, I'm going to get to the answer, so...
-5 or -6?
That is a 6. It's -2 over 3 minus the square root of 6. That's a 6.
Oh my gosh.
Just, shh. All right, so I'm going to freeze it here. I'm going to use my conjugate to simplify this thing. You do the same. Yeah, just be quiet and do it. So I don't know if you guys ran into this while you were doing it, but once you kind of get the hang of this a little bit, not a lot of it, but a little bit, you could probably skip this step right here. Because you know these things are going to multiply, right? You could probably go right from here over to there, right? So, because that's what I did on the next one here. I just skipped over that middle step there because I could tell I needed to multiply. So. Every year I get them from people just at random times. I divided. Negative 6 divided by 3 is negative 2, and negative 2 divided by 3 is negative 2/3. Got to this point?
I got there. I paid attention.
Yeah, that's good. That's good. If you left it here, it's not, well, I guess technically, it satisfies those three things, right? There's no more roots in the bottom, and yeah. This is kind of the more accepted way of doing it, but it's not a big deal. You did, wait, shh. You did what?
I did negative 8 square root of 6 over negative 6 minus 2.
Oh, okay, so, good question. Shh. He said that he had negative 8 square root 6 on the top because negative 6 minus 2 is negative 8. Okay? So, again, be careful because think of square root of 6 as kind of like a variable. It's like x. If you had negative 6 minus 2x, could you put those two things together?
No.
They're not like terms, right? So anytime you have a number multiplied with a root and then a number that's not, they're not technically like terms, and so you can't put those things together. So that would have to stay separated there. I divided. I took each one of these two numbers and divided. All right? Okay. We're going to move forward unless anybody else has any questions about this process for me. Yes? Negative, say that again?
Negative 2 square root of 6 all over 3.
Oh, that's the same at the end there. Yep. All right. Okay, shh. Since we're talking about like terms, it's kind of a nice little segue into this next thing. Adding and subtracting roots to each other, we can only do if we have like terms. So I'll give you a quick example of what I'm talking about. And this is where I'm going to stress again. Think of the roots as being like a variable.
What did you say about like terms? Like
You can only add or subtract if they are like terms.
so the roots have to be the same.
They have to be exactly the same. Okay? So think about this. Let's say, pretend the square root of 2 is actually just x. Okay? So if I had 5x plus 3x, what would that be? 8. Just 8x, right? 5x plus 3x is 8x. I got 5 of them plus 3 more of them. I've got 8 altogether, kind of a thing, right? No, well, not really. So 5 root 2 plus 3 root 2 is 8 root 2. Okay? I've got 5. Think of it this way. I've got, think of the square root of 2 is like a little block or something. Okay? I've got 5 little blocks over here, and I've got 3 of my little blocks over here. I add them together. I have 8 square root of 2 blocks when I'm done, kind of a thing. Okay? It's that idea. All right? Now, if the little blocks don't match, let's say one was the square root of 2 and another one was the square root of 3, different blocks. I can't put them together. Okay? So they're not like terms in that case. So there has to be not only the same type of root, but exactly the same root from one to the other to be able to add or subtract them together. Okay? So that's how we're going to deal with the next one. They're not going to be the same, but we're going to make them the same. Yeah. Mm-hmm. All right. Shh. Okay, so let's say we've got the square root of 20 plus 7 square root of 5. Square root of 20 and square root of 5 are not the same exact roots, but I can simplify one of them to help me here. Square root of 20 simplifies, right? Okay. Guys, really stop talking. So, square root of 4 times the square root of 5. We did this yesterday. This would be 2 root 5. And now, after I simplify the 1, now I've got two things that are the same that I can add together, right? I got the same kind of roots. Both of them are root 5. 2 root 5 plus 7 root 5 is what? 9 root 5. Right. Sometimes you just have to do a little upfront work to get it there. Be done. Now, it's not always the case where the things are going to actually add together, but sometimes they do. So let me show you another one. This isn't just with square roots again. Remember, we're talking nth roots. So what if we had like a cube root or something? So if we had like the cube root of 54 minus the cube root of 2, okay, you can't make that the cube root of 52, okay? They're not the same type of cube root, so it doesn't work. However, one of the two of those things I can break down like we did yesterday. 54. What's a perfect cube that goes into 54? In fact, we might have done that exact 27, right. 27 times what is 54? 2. So I can break that 54 down into a 27 and a 2 in cube roots.
See, how are we supposed to know that, though?
You study that list of perfect cubes I gave you yesterday. All right, so I can take the 54 down. What's the cube root of 27? 3. So I have 3 cube root of 2 minus cube root of 2. Nope. It's 2 cube root of 2. Think of it as a variable. I got 3 of them. I'm taking 1 away. How many are there? 2, right? So 2 cube root of 2. Question, Liz?
I'm still kind of confused, like, okay, the cube of 54
The cube root of 54.
would be,
What number do you multiply by itself 3 times to get 54? Is the cube root of 54. But there's not a nice even number that does that, right? So we can't actually say that the cube root of 54 is this one number. What we can do, though, is we can break it apart into a smaller one.
it's like you can break apart square root, do cube root.
Right, same idea.
Wait, so where'd you get the 27 from?
Okay, so 27, 27 is what's called a perfect cube, because 3 times 3 times 3 is 27.
Cube times, does it have to be perfect cube times something?
Mm-hmm. Right, just like over here, I had to do 4 and 5, because 4 is a perfect square. Over here, I had to do 27 and 2, because 27 is a perfect cube. Otherwise, this doesn't work. Got it? Yep.
So the answer is just cube root 2.
Yes.
There's basically one and the like.
Yep. Yep. There's one of them. So this is 2 cube root of 2. All right. So as long as the type of root is exactly the same, you can add or subtract. Okay, that's the idea with all the addition, subtraction stuff.
Yeah, but when they're not the same, then what?
Then you just got to leave it. There's nothing you can do.
Are you sure?
I'm sure.
We're not going to go along and say, remember when we were doing this and that? Well, here's the thing.
No, this one doesn't change later.
All right. Because he pulled that trick a few times.
I know. We kind of, mathematicians, we're jerks that way. What are you looking?
You know how 54 divided by 2 gives you 27?
Yeah.
So technically, could you just do that every time? Like, you know, like take the bigger number and divide it by the little
Oh. Yes. Yeah, to find the one that's going to work. Now, here's the thing. That does work, assuming that it is possible to come up with ones that are the same, and also assuming that this one can't also be broken down. Because what if this was like the square root of 20 and this was like the square root of 100 or something? And then you'd be kind of stuck because one's not one that goes into the other one or something. But in any event, in general, yeah, that works most of the time. All right, so we're going to talk variables next because up to this point we've just been using numbers in these things, right? Now we're going to throw some variables at you and try it with that. Alrighty? So this guy. The nth root of x to the n. What is it?
X.
X. I think that's pretty straightforward, right? Okay. What about so what if I have the nth root of x to the 2n? It's x squared. Okay, now why is it x squared? Hmm?
What I'm
So,
very
you're telling me, wait. If n was 1,
Yeah.
that means it would just be x, right? It
Yeah.
would just be x.
Yeah.
If n was 1,
Yeah.
right?
Yeah.
Now, if n was 2,
Uh-huh.
would it still just be x?
No, it'd be x squared. You talking about this one up here or this one down here?
I'm talking about that one.
This one right here, then it would be x squared if n was 2.
So no matter what,
Oh, so you were talking about this one to begin with too then?
yeah.
If n was 1, it would still be x squared. If n was 3, it would be x squared. If n was a billion, it would be x squared.
It's already square rooted.
It's not a square root, it's an nth root. This,
very confusing.
let me show you an example of each of these, and I'll hopefully calm you down just a little bit. Okay?
You're just throwing gibberish at it.
It's not gibberish, it's true statements.
Not true, but I worked really hard.
Okay. So, an example of the first one, hopefully not too crazy hard. 5th root of x to the 5th is x. Okay. Second one. So what's the 5th root of x to the 10th? X squared. Why is that? Here's why. I'm going to prove it to you, and you tell me if each step makes sense. Okay. Are you with me so far?
Oh yeah, it's square. Okay.
It's x to the 10th, and we talked about this, how we can break them up, right? If it was x to the 10th, can't I just break it into an x to the 5th and an x to the 5th then? Because 5 plus 5 is 10, right? When you multiply things that have powers, you add the powers, right? That's a property we talked about yesterday. Okay? So x to the 5th, just hold on. So x to the 5th is x to the 10th. So I can break up x to the 10th in two of those guys. And we already said, what's the 5th root of x to the 5th? X. So each of these are x. X times x is what? X squared. Okay. Here's another way to look at it.
Wait, but you're telling me 5, that doesn't make any sense. X times x equals x squared. So you're telling me 5 square root of x to the 10th is equal to x squared.
Absolutely.
Who's boss
Mm-hmm. Yes?
Okay, so for the first example,
Mm-hmm.
5,
Yeah.
the answer is x, and then
Mm-hmm.
5 and 10.
Mm-hmm.
Could you just divide?
Oh, hold that thought. Yeah. All right, so here's another way to do it. She was about to steal my thunder. All right. Remember how we talked yesterday about how you can take a root, an nth root, and make it into a fractional exponent? Guys, over in the corner, be quiet. I'm about to separate you all. Okay, remember how we talked about an nth root can be turned into a fractional exponent instead? It's an alternate way to do a root. If I have a 5th root, couldn't I then just do this? We all agree with that? Yeah? Yeah, right? Okay, so power of a power. What do you do with the powers?
You
multiply them.
You multiply them. What's 10 times 1/5? 2.
Wait, I have a question.
Yes. Fifth root. 1/5 power. No, that's a 5. Sorry. It's supposed to be a 5.
Oh, okay.
It's supposed to be the same problem again. This and this are the same thing. Yeah. Yeah. So, yeah, you can take this number and divide by that number, and it's that power when you're done. Now, here's the kicker. These have to be divisible then. What if this was a 10 and this was a 7? Could we do this? Mm-mm. Okay? So we're gonna come across a few of those as we go down the road here a little bit. But for now, I need to be sure that you're okay with this at least. Okay? Where you can divide them and do it. Let me give you a few examples for you to try on your own here and see if you can use this same idea to help you come up with some answers. Okay? All right, so why don't you do the third root of y to the 9th and the 10th root of x to the 50th?
All right.
Using this idea.
So it'd be 5. 5 x good.
So you're doing the second one then, I'm guessing?
Yeah, I'm doing the second one.
Okay.
And now the first one would be
Yeah.
Some of them have like big multiplication or division.
Oh, that's okay.
That's what
That's okay.
I was just
All right. Everybody with me? We're good there? Okay. All right. We're going to use this whole take the two numbers and divide them to get to the new power idea in the midst of some other ones. It's like one step on the way to the end. So I wanted to be sure we were okay doing that before we moved along. All right? Because we're going to be simplifying some expressions here. We're going to have to do that. So, oh, you're looking at hers? Okay. So, hold on to your butts. Here we go. So, we're going to do the fifth root of 4 a to the 8th b to the 14th c to the 5th. All right, we're going to simplify that thing.
Wait, you already give us the answer to the other one?
Hmm?
Did you already give us the answer?
Yeah. It was y to the 3rd and x to the 5th.
Okay, that's what I got.
All right.
What?
It is the fifth root. Write it down. Write it down. We can do this. It's the fifth root of 4a to the 8th, b to the 14th, c to the 5th. That is correct. We'll get there in just a minute, though. All right, so remember how that these two things need to be divisible with each other in order to do this? C is good, but a and b we're having problems. Okay? So what I'm going to do is I'm going to break it apart into two square roots, or two fifth roots, rather, so that one of them, none of the variables have any problems. Okay? So, see if you can follow what I'm doing here, okay? I'm going to do the fifth root, a to the 5th, b to the 10th, c to the 5th, and then I'm going to multiply that with the fifth root of 4a to the 3rd, b to the 4th, and that's it. Okay, so somebody tell me, what did I just do? How did I get that? Yeah.
You made the first one divisible by 5 and you throw the extra number.
Right. I took the variables out of that thing and made sure that all of the powers were divisible by 5, at least as much as I could, and then the leftover crap is in the other one. Okay? So, this fifth root right here, using the ideas that we just talked about, you should be able to do that, right? We can get new powers for A, B, and C off of that thing because each one of those are divisible by 5. It works. Okay? Yep.
Can you also do like e to the fifth, like e to the ninth?
You could, but I can take out a couple of B's though. I can take out 10 of them because 10 is still divisible by 5. So I want to take out as much as I can. Otherwise, I'm going to have to keep repeating this process over and over again as I go. Okay? So what do I get when I do the fifth root of all of this stuff here first? Yeah.
How'd you get A to the fifth?
Because I had A to the 8th, and A to the 5th, and A to the 3rd make A to the 8th. So I just broke it apart. It's multiplication, so I can take them apart like that.
So you had A to the 8th, then you had A to the 5th, and then A to the 3rd.
Right. Because remember, when you multiply powers together, the exponents add, right? So if I'm going to break it apart, as long as I have a 5, then I need a 3, that makes my 8, I'm good. So then, the rest of this stuff, fifth root of 4, A to the 3rd, B to the 4th. I can't take the fifth root of any of that stuff because it's not, the 4, I don't know the fifth root of 4 to start off with. And then this A to the 3rd, B to the 4th, those powers aren't big enough for me to take a fifth root of them and do anything with it. So this is actually my answer. Believe it or not, this is considered the simplified version of what we started with. It is. It is. But what is underneath the radical is smaller. And that's the key. What's underneath the radical is smaller. Yeah.
So basically, the answer when taking 5 divided by 5, which is 1 plus A,
Mm-hmm.
5 divided by 2, which is B squared, and then 5 divided by 5.
You're dividing each of those exponents by 5 because it's a fifth root. It's just everything that's, you can't do anything with it. It's all the leftover stuff, but these powers aren't high enough to do anything with this fifth root then. So we got to just leave it. Okay. Okay, let's try one more like this, guys. See if you can do one more on your own here. I've got a few more examples after this, but then we're done. Few more. Few usually means 3. That's a cube root, yep, of 8, A to the 11th, B to the 15th. All right, so let's try that, okay? I'll freeze it, see if you can do this one on your own. Cube root of 8, A to the 11th, B to the 15th.
But nothing equals 11.
So break it apart like we did the top one.
Yeah. It just has to be 1 and 11. Oh, but you have to add. Never mind. So
Okay.
it would have to be 9 and 3.
9 and 2?
No.
Because 9 plus 2 is 11? Is that what you're talking about? Yeah. It's got to be 9 and 2. Yeah. Do you know the cube root of 8?
2.
Because it didn't take the cube root of 8. Actually, after school, he got me the Tootsie Pop. It was delicious. Yes? Okay, good question. So, the question was asked, okay, and correct me if I'm wrong, but why is there a 4 left over in this one, but not the 8 in this one?
Like the division when you make the A fifth, you tend to why is there no 4?
Aha, okay. So, yeah, in this one, in the first example, the 4 didn't come along into this first fifth root, but the 8 did in this one. The reason is, if you're capable of taking the cube root of it, you put it in that first one. I can take the cube root of 8. It's 2. Okay? This first one, can I take the fifth root of 4? Nope. So I got to leave that guy behind. So I'm only taking the stuff I can do in that first one. Okay? So cube root of 8, a to the 9th, b to the 15th, I can take care of all 3 of those. Cube root of 8 is 2. Cube root of a to the 9th is a to the 3rd. Cube root of 8, or b to the 15th is b to the 5th. And then I got a cube root of a squared to finish it up. Okay? That's as simplified as I can get that thing. All right. So, like I said, a few more examples. These other ones are going to look a little different than these. Now, these are going to have some other issues with simplifying. These guys, these were kind of like those first ones we did when we were simplifying roots yesterday, where they couldn't have perfect nth powers within them. Okay? This is doing that same idea, but with the variables. Now we're going to deal with the whole fraction business again, but with variables. Okay? So what if we had something that looked like this? What's the issue that this one has where it's not simplified yet? Denominator has a root in it. Okay, there's a cube root in the denominator. And what did we do to take care of that before? You multiply it by the same thing over itself, whatever that happened to be, so that we got a perfect whatever on the bottom. This time I have a cube root on the bottom. I need a perfect cube. Is y to the 8th a perfect cube? No. What is, or just a little bigger than 8 that I can take a cube root of? 9. Okay. So what could I multiply by to get a y to the 9th in there? It would have to be a cube root to keep it, a cube root times a cube root. But the cube root of what? Y. Exactly. The cube root of y multiplied by the cube root of y to the 8th is the cube root of y to the 9th, and that I can do, right? So you got to ask yourself, what do I need to multiply by to get this thing to a place where I can actually take the cube root of it? How much more do I need? In this case, it's just the cube root of y. It's what I need. All right. Now, if I do that in the denominator, I have to do that in the numerator as well, right? So this fraction, I'm going to need to put another cube root of y on top here. And let's see what we end up with. So in the numerator, I've got x cube root of y. And in the denominator, I have the cube root of y to the 9th. Okay, and what is the cube root of y to the 9th? Y to the 3rd power. So I have x cube root of y on top still, all over y to the 3rd. This, yes, is simplified, even though it doesn't really look maybe any more simple than the first one. But it is no longer violating that rule that says you can't have any roots in the denominator, so there it is, okay? So again, you're going to multiply by something over itself, but it has to be something to give yourself a perfect, in this case, cube, could be a square, fourth, or whatever, in that denominator then. Okay? All right, we got 2 more here, and then we're done. What?
Hold on. Oh, yeah, that's the same thing that we were doing earlier.
Yeah. It's just with variables instead of numbers this time. This is something that is the same as what we've been doing, except now I'm writing it with fractional exponents instead of the root symbols. Okay? If anything, I think this is easier. Whoa. You haven't done anything yet. Chill out. All right, so remember what we talked about. There's this exponents that if we're dividing, what do you do with the exponents? Nope. There you go. If we're dividing powers, guys, you subtract exponents. Okay? So, now, that's only if we have powers. Notice how there's a 6 and a 3 that are both coefficients here. Those aren't powers. We don't subtract the 3 from the 6. What do we do with the 6 and the 3? You actually divide those, right? So 6 divided by 3 is 2. And then we go through each individual variable and subtract their powers, okay? So we have x and x to the 1/2. So what is that? X to the power of 1/2. 1 minus a half, right, is what we're doing there essentially. And then we've got 3/4 minus a half on the y. What's 3/4 minus a half? A quarter. So it's y to the 1/4 power.
That's our answer. So you're telling me that's our answer? But now, that's all we have to do.
Yeah.
6 and 3. What if those variables aren't divisible?
Oh, good question. So,
You have to do that, aren't you?
yeah, but it's not as bad as you might think. What if, okay, so he asked the question, what if the 6 and the 3 were not divisible? Okay, don't change it in your notes, but I'm going to change it on here real quick and make it that way and see how things change. So this is not going to be a 2 anymore.
Make it 5, you won't. What?
I said, don't change yours. He asked the question, so I'm going to show you what happens. Okay? What if the two numbers are not divisible? Okay, I got a 6 and a 5. What's 6 divided by 5? 6/5. It's a fraction, right? I'm not even kidding you.
X should be 1 and 1/5. It's got to be proper. It's got to be
No, 6/5, x to the 1/2, y to the 1/4. That's it. Just leave it as a fraction, okay?
That's all we have to do.
All right, guys. Yes. Oh, pay attention. I said don't change it in your notes. I'm going to make it a 5 and show you what happens, but it's fine. Oh, whoops. All right, last one. We're going to simplify this. It's a subtraction problem. Remember we talked about with subtraction problems? We need to have the same exact type of root to be able to do that. Okay? Square roots here that I can simplify up a little bit like we were doing up at the top. So I got this square root of 9y to the 5th. Let's ignore the rest of it for a second and just look at that. So, can we take the square root of 9? Okay, so that's a 3. And then the rest of this thing, w to the 5th, is that divisible by 2? Because remember, a square root is actually 2. No. So what could I do with that w to the 5th to break it up? Yep, we'd have a w to the 4th and then just a w.
Where'd you get just the W?
Because that's what w to the 1st. And 4 plus 1 is 5. So that would work. Okay. So now the other one.
Yeah, but can't you keep doing that?
No, you can only do it once. Because as soon as you take the square root of w to the 4th, that's as far as you could go with it. Over here, square root of w to the 3rd. Can I take the square root of w to the 3rd? Because 3 is not divisible by 2, right? I could take out a w and make it a w squared and a w, right? Hold that thought. Hold that thought. All right, so let's take the square roots that we can take now, okay? Square root of w to the 4th is what? W squared. So we've got 3w W squared square root of W. What's the square root of W squared? W. W I can multiply with this one. That's W squared.
What is this?
Yeah, but now you have the square root of W. So, but those cancel. They don't cancel
So
out.
the answer is 3.
Infinity.
What? 55 squared, isn't it?
Oh.
If you think you know the answer, raise your hand. We can check it. Mr. Brookhouse?
2W squared to the squared W.
That's right. Yep. 2W squared square root of W.
Did mathematicians just want to
Hey, we are.
that's the correct term.
We are those, yeah. So, this is all the variable stuff in there. I'll be honest, guys. I appreciate your willingness to jump into this stuff. This is about as ugly of algebra as we're ever going to do. Ever going to do. Okay?
Until Thursday.
Yeah. Till next week, then we're going to do something more fun. No, honestly, this stuff, as math teachers, we loathe teaching this stuff. It's so dry. But you guys had a good attitude and it went okay, so thank you. Your reward is some more practice with it.
But the thing is, I really don't. I don't know how to do that.
Why is it?
What?
Why is it just one square root of W? See how there's 2 of them there?
Hold that. I'll answer that in a second. All right. Shh. Now keep in mind. Hey, relax. Now keep in mind, this isn't due until Thursday, right?
Oh, thank goodness.
And we have all class period tomorrow to work on this stuff if you so choose. So chill out, rein it in, exhale. It's okay. All right. And with that, I'm going to stop my recording.